Hello everyone. Today we will study cardinality of sets. First of all, let's look at a simple example about cardinality of sets. Look at a simple example first. N is the set of all natural numbers. That's integers from 1, 2, 3, 4 go up to infinities. That's the set of natural numbers. And what's the set of 2n? 2n represents a set that we multiply each element in a set by 2. 2n represents a set that we multiply each element in a set by 2. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and so on. So you can see that n is the set of all natural numbers. N is the set of all even natural numbers. You can see that every element in the set is even. Now my question is, which set has larger cardinality? Which set has larger cardinality? Which set has larger cardinality? We can clearly see that 2n is a subset of n. 2n is a subset of n. We can see that, clearly see that 2n, the set of even number, is a subset of n. 2n is a subset of n. So we may think that 2n has less cardinality than n because it's a subset of n. It's a subset of n. So we may think of 2n has less cardinality than n. But on the other hand, is this true? On the other hand, remember the construction for 2n. If I multiply each element in a set by 2, the number of elements in a set should be the same. On the other hand, if I multiply each element in a set by 2, the number of elements in a set must be the same. Is this true? If I multiply each element in a set by 2, the number of elements in the set should be the same. But 2n is a subset of n. So, which one is true? So, in order to find out the relationship between n and 2n here, let me introduce the cardinality of sets. Rule for cardinality. Let A, B be two sets if there is an injection. If there is an injection means one-to-one function. If there's a one-to-one function from A to B, then we say cardinality of A is less or equal to B. If there's an injection function, if there's an injection from A to B, then we say cardinality of A is less or equal to B. Injection means one-to-one function. If there is a bijection means one-to-one n on 2. If there's a bijection from A to B, if there's a bijection from A to B, then we say set A has the same cardinality as set B. If A cardinality of A is less or equal to B, and cardinality of A is not the same as B, then we say A cardinality of A is strictly less than cardinality of B. Now, for these rules, let me show you some simple examples. Let A be a set of A, B, C. Let B be a set of 1, 2, 3, 4, 5. Assume function f is a function from A to B, and f assign A to 1, assign B to 3, assign C to 4. We can see that this function f is a one-to-one function. It assigns each element in set A to a different element in set B. This function is one-to-one, and we can see that cardinality of set A is less than cardinality of set B. If there's a one-to-one from A to B, then we say cardinality of A is less than cardinality of B. We can see that here. If there's a one-to-one from A to B, we can see that cardinality of set A is less than or equal to cardinality in set B. Now, what if there's a bijection? Another example, let A be the set of A, B, C, D. Let B be the set of 1, 2, 3, 4. For example, G is a function from A to B, such that G assign A to number 4, assign B to number 1, C to number 2, D to number 3. And we can see that this function assigns each element in set A to a different element in set B. It is one-to-one. And every element in set B has an inverse image. So the range of G is the same as codomain of G. This function is onto. Every element in set B has an inverse image. This is an onto function. Since G is a one-to-one and onto function, it's a bijection. We can see that cardinality of set A and set B is the same. In addition, this argument works for infinite sets. Assume A is in the set of, for example, A1, A2, A3, A4, A5, and so on. B is in the set of B1, B2, B3, B4, B5, B6, B7, B8, and so on. Let f be a function from A to B. Assume I assign A1 to B1, A2 to B3, A3 to B4, A4 to B6, A5 to B8. You can see that this is a one-to-one. This is a one-to-one function. And we can also see that set A has cardinality of set A is less than or equal to cardinality of set B. You can see that there are some actual elements here. There are some actual elements in set B. Each element in set A assigned to an element in set B. And in set B, there are some actual elements here. So we can clearly see that cardinality of set A is less than or equal to cardinality of set B. So if there's a one-to-one function from A to B, cardinality of set A is less than cardinality of set B. This argument works for infinite sets, also works for infinite sets. Now let's look at a bijection. Let A be the set of A1, A2, A3, A4, A5. let B be the set of B1, B2, B3, B4, B5, and so on. So they are both infinite sets. Say G is a function from A to B. Let G assign A1 to B1, A1 to B2, assign A2 to B1, assign A3 to B5, assign B4 to B3, assign A4 to B3, assign A5 to B4. We can see that this function is a one-to-one and onto function. If this one is a one-to-one and onto function, we assign each element in set A to one element in set B, and each element in set B has an inverse image in set A. They have exactly the same cardinality. Every element in set A is assigned to an element in set B, and every element in set B has an inverse image in set A. So they have exactly the same number of elements. If there's a bijection from A to B, there are exactly the same elements in set A and set B. So this definition works for both finite and infinite sets. Keep this in mind. Now we know the rule for cardinality. Let's go back to this old example here. Let's compare the cardinality in N, in the set of N and the set of 2N here. When we construct the set of 2N, we multiply each element in set N by 2. So it looks like there is a bijection from N to 2N. If there is a bijection from N to 2N, then they must have the same cardinality. So let's prove it. Show that the cardinality of set N is the same as cardinality of set 2N. To show two sets has the same cardinality, we must show that there's a bijection from A to B. Bijection means we show a one-to-one function from A to B. From here is from N to 2N. So proof. So by construction, we see that we multiply each element in N by 2. So we can say let function f from N to 2N be defined as f of x equal to 2x. The function from N to 2N be defined as f of x equal to 2x. Then to show two sets have same cardinality, we must show f is one-to-one and onto. Next, we try to show f is one-to-one and onto. To show f is one-to-one, let S1, S2 belong to the domain. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Then I substitute S1 for x. 2S1, I substitute x2 for x. I have 2s2 here. If I divide both sides by 2, I have s1 equal to s2. So f of s1 equal to f of s2 implies s1 equal to s2. That means f is one-to-one. Next, we try to show f is onto. So let y belong to the codomain. Let y belong to the codomain. Then we can see that in the codomain every number is even. Then we know y is even. Since y is even, then we know y over 2 is an integer. Since y is even, so then y over 2 is integer. Let x equal to y over 2. Let s equal to y over 2 in a domain. Let s equal to y over 2 in a domain. Then f of x equal to f of y over 2. If I substitute y over 2 for x, I get 2 times y over 2, which equal to y. So since f for all y in a codomain, there's x in a domain such that f of x equal to y, then we know f is on 2. Since f is 1 to 1 and on 2, then f is a bijection. Therefore, f is a bijection. And since f is a bijection from n to 2n, then we know n and 2n, the set n and 2n has the same cardinality. So the set of n and 2n has the same cardinality. Since there's a bijection from n to 2n, the set n and 2n has the same cardinality. Next, let me introduce a theorem about cardinality. Let A and B be sets. If A is a subset of B, then cardinality of A is less or equal to cardinality of B. Can we prove it? Let's try to prove it. To show A has smaller cardinality than B, we must show that there's a one-to-one function from A to B. To show A has less cardinality than B, we must show that there is a one-to-one function from A to B. So let's construct one-to-one. Let's construct a one-to-one function here. Let f from A to B be defined as f of x equal to x for all x in A. The function f from A to B be defined as f of x equal to x for all x in A. How it looks like, how the function looks like. Let me show you the picture. So f is a function from A to B. A is a subset of B, so A is actually inside B. F is a function from A to B. Let's assign each element to exactly the same element in set B. So x1, x2 to s2, x3 to x3. F is a function that assigns each element in set A to exactly the same element in set B. Since A is a subset of B, every element in set A must be here. So f assign s1 to s1, s2 to s2, s3 to s3. So that's how I define function f. Next, we need to show that this function f is a one-to-one function. Next, we need to show that this function f is a one-to-one function. So let x1, s2 belong to set A. Assume f of s1 equal to f of s2. Then, by its definition, f of s1, if I substitute s1 here, I get s1. For f of s2, if I substitute s2 here, I get s2. Then we have s1 equal to s2. Since f of s1 equal to f of s2 implies x1 equal to s2, then f must be one-to-one. Since f is one-to-one, cardinality of set A must be less or equal to cardinality of set B. Another theorem. Let f be a function from A to B if f is one-to-one, then cardinality of A is the same as the cardinality of the range. If f is 1 to 1, then cardinality of A is the same as cardinality of the range. Let's try to prove it. So to show two sets has same cardinality, we must show that there is a bijection from A to the range of f. We want to show that there's a bijection from A to the range of f. So let G from A to the range of f be defined as g of x equal to f of x for all x in A. Then we try to show G is 1 to 1 and onto. So let x1, s2 belong to A. Then assume G of s1 equal to G of s2. G of s1, if I substitute s1, I get f of s1. For G of s2, if I substitute s2, I get f of s2. Since f is 1 to 1, since f is 1 to 1, then since f is 1 to 1, then f of s1 equal to f of s2 implies s1 equal to s2. So also g of s1 equal to s2, we also get the same conclusion here. We start from g of s1 equal to s2, we eventually prove that s1 equal to s2. So g is 1 to 1. Next, we try to show g is onto. Let y belong to f of A. Let y belong to f of A. By definition, f of A means there exists x in A. Let's write it this way. Then y equal to f of x for some x in A. That's the definition of f of A. F of A, by definition, is the set, assume f is a function from A to B. F of A is the set of all y in B, such that y equal to f of x for some x in A. That's the definition of f of A. Y equal to f of x for some x in A. Then so g of x, so g of x is the same as f of x. It's the same as y. So for all y in f of A, there's x such that g of x equal to y. So g is onto. Since g is 1 to 1 and onto, therefore g is a bijection and since g is a bijection from A to f of A, then the set cardinality of A is the same as cardinality f of A. Let me show you a picture. It will make more sense to you. Let me show you a picture. Let F be a bijection from set A to set B. Assume set A is the set of A, B, C, D. Assume B is the set of 1, 2, 3, 4, 5, 6, 7. For example, F is a one-to-one function. Let us assign letter A to number 2, assign letter B to number 3, assign letter C to number 4, assign letter D to number 5. So in the set 2, 3, 4, 5, that's the range of F. Let's call F of A the range of F. The set 2, 3, 4, 5 is the range of F. Let's call F of A. And we can see that that's a one-to-one function. If I define G equal to F, if I define G from A to F of A, the same as F. If I define G from A to F of A, the same as F, then this function G, you can see that it's one-to-one, and it's also on2. Since we only consider the codomain is F of A, G is also on2. G is one-to-one and on2. And we can also see that these two sets A and F of A has exactly the same cardinality. Next theorem. Let A B and C be sets. First statement says if cardinality of A is less or equal to cardinality of B, and cardinality of B is less or equal to cardinality of C, then cardinality of A is less or equal to cardinality of C. If cardinality of A equal to cardinality of B, and cardinality of B equal to cardinality of C, then cardinality of A equal to cardinality of C. Let's prove it. Proof for the first statement. Cardinality of A less or equal to cardinality of B. By its definition, that means there is a one-to-one function f from A to B. There's a function from A to B. There's a function f from A to B, such that f is one-to-one. Cardinality of B less than C implies there's a function g from B to C such that g is one-to-one. Then we know the function g composition f is a function from A to C. Since f and g, they are both one-to-one, then in section 2.3 we prove a theorem that says if f and g, they are both one-to-one, their composition function is also one-to-one. Then composition g of f is also one-to-one. That's a theorem we proved in section 2.3. Then since the function g of f is a function from A to C and g of f is one-to-one, then cardinality of A is less or equal to cardinality of C. g of f is a function from a to c and it's 1 to 1. So by definition of cardinality, the cardinality of A is less or equal to cardinality of C. Next, proof for the second statement is very similar. Cardinality of A equal to cardinality of B. That means there is a function f from A to B such that f is a bijection. Cardinality of B equal to cardinality of C. That means there's a function g from B to C such that g is a bijection. Then the competition function g of f is a function from A to C. Since f and g, they are both bijections, then in sections 2.3 we prove a theorem that says composition function of two bijections is a bijection. Then the competition function g of f is also a bijection. Then by definition of cardinality, we know that cardinality of A is the same as cardinality of C. Since there's a bijection from A to C, since there's a function from A to C, and this function is a bijection, the cardinality of A is the same as cardinality of C. Next, let's do some example about cardinality of sets. Let A be the set of natural number. Let B be the set of natural number plus a 0. Let B be the set of natural number plus a 0. So here we can see that A is a subset of B. A is a subset of B. Therefore, by one of the previous theorem, cardinality of A is less or equal to cardinality of B. Now my question is cardinality of A strictly less than cardinality of B, or cardinality of A equal to cardinality of B? Think of this question. My answer is cardinality of A is the same as cardinality of B. To prove it, that's easy. Let function f from A to B be defined as f of x equal to x minus 1. You can verify this function is a 1-to-1 and onto function. Let me show you the picture, it will make more sense. Let A is a set of natural number, so it's a set of 1, 2, 3, 4, 5, and so on. B is the set of natural number plus a 0. So B start from 0. We have 0, 1, 2, 3, 4, and so on. this function f from a to b, f from a to b is defined as x minus 1. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. So you can see that this is a one-to-one and onto function. So since there's a one-to-one and onto function, there's a bijection from a to b, then cardinality of a is the same as cardinality of b. Since there's a one-to-one and onto function, since there's a bijection from a to b, cardinality of a equal to cardinality of b. So you can verify by yourself. You can verify by yourself and show this function is a one-to-one function. In this function is a one-to-one and onto function. Next example. Let A be the set of natural number. Let B be the set of all odd integers. Let B be the set of all positive odd numbers. Let A be the set of natural number. Let B be the set of odd natural numbers, that means positive odd numbers. So we can clearly see that B is a subset of A. So we can clearly see that here B is a subset of A. Therefore, cardinality of B is less or equal to cardinality of A. Now my question is cardinality of B less than cardinality of A, or is cardinality of B equal to cardinality of A? Think of this question. Think of this question. My answer is cardinality of A, cardinality of B equal to cardinality of A. Let's prove it. Let f be a function from a to b, be defined as f of x equal to 2x minus 1. Then you can verify by yourself. This function is one-to-one and onto function. Then f is a bijection. And hence, since there's a bijection from a to b, hence cardinality of a is the same as cardinality of b. Let me show you a picture here. It makes more sense. Let me show you a picture. A is the set of natural number 1, 2, 3, 4, 5, 6, 7, and so on. B is the set of positive odd numbers. B is the set of positive odd numbers 1, 3, 5, 7, 9, 11, 13. Function f from a to b I define as 2x minus 1. 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5, and so on. And we can see that this is a one-to-one and onto function. Of course, I need to prove it. Picture is not proof. And we can see that this is a one-to-one and onto function. Then, since there's a bijection from a to b, then cardinality of a equal to cardinality of b. And same thing for the previous question. I forgot to say that f of x from a to b defined as f of x equal to x minus 1. You can also verify that f is a bijection. Then we know that cardinality of A equal to cardinality of B. Next example. Consider a set of natural number and a set of integer, do they have the same cardinality? Do they have the same cardinality? Natural number contains only positive integers. An integer, the set of integer contains positive integer, negative integer, and zero. Do they have the same cardinality? My answer is yes. How do we prove it? How do we prove it? To show two sets have same cardinality, we must show that there is a bijection from n to z. So let's try to find a bijection first. N is the set of all positive integers, 1, 2, 3, 4, 5, 6, 7, and so on. Z is the set of positive integer, negative integer, and 0. So let me write Z in this way. 0, negative 1, 1, negative 2, 2, negative 3, 3, and so on. Let me find a function f. Let me find a function f from n to z. Let map 1 to 0. Let's deal with odd number first. I want to map 1 to 0, 3 to 1, 5 to 2, 7 to 3. So I can say let f from n to z be defined as f of x equal to, for odd numbers from 1 to 0, 3 to 1, 5 to 2, 7 to 3, I can take, those are odd numbers, so I can take odd number minus 1 over 2 if x is odd. For odd numbers, I can take odd number minus 1 over 2. 1 minus 1 over 2 is 0. 3 minus 1 over 2 is 1. 5 minus 1 over 2 is 2. 7 minus 1 over 2 is 3. Now for even number, I try to assign 2 to negative 1, assign 4 to negative 2, assign 6 to negative 3. For even number, I can take negative x over 2. So for number 2, I take negative 2 over negative 1. Actually, I take negative 2 over 2, I get negative 1. For number 4, I take negative 4 over 2, I get negative 2. For number 6, I take negative 6 over 2, I get negative 3. If x is even. So you can see that in the picture, you can see that this function is 1 to 1 and onto. In the picture, you can see that this function is 1 to 1 and onto. Now let's prove it. Let's prove it. So first of all, let's try to show f is 1 to 1. For 1 to 1, let x1, s2 belong to the domain. Assume f of s1 equal to f of s2. Then there are two cases. They must either be both positive or both negative. Then we have two cases. Case 1, they are either both greater or equal to 0, or they are both less than 0. Case 1. If they are both greater than 0, greater or equal to 0, since x minus 1 over 2 is always greater than 0 when n is a natural number, and negative x over 2 is always negative when n is a natural number. If f of s1, f of s2 is greater than 0, then both s1 and s2 must be odd. both s1, s2 must be odd. So since f of s1 equal to f of s2, I substitute s1, substitute s2, I have x1 minus 1 over 2 equal to s1 minus 1 over 2. If I substitute s1, I get s1 minus 1 over 2. If I substitute x2, I get s2 minus 1 over 2. Then we try to show s1 equal to s2. I can multiply both sides by 2. I get s1 minus 1 equal to s2 minus 1. Then I can add 1 to both sides. I get s1 equal to s2. Case 2. If both f of s1 equal to f of s2, if they are both less than 0, then if they are both less than 0, then both x1, s2 must be even. If f of s1 or f of s2 is less than 0, then they must have no form negative x over 2. Then both s1, s2 must be even. Then both s1 and s2 must be even. So if I plug in s1, s2, I have negative x1 over 2 equal to negative x2 over 2. If I multiply both sides by negative 2, I have s1 equal to s2. If I multiply both sides by negative 2, I have s1 equal to x2. So since in both cases we have s1 equal to s2, then we can say f is 1 to 1. Next, we want to show f is onto. So let y belong to the codomain. Let y belong to the codomain. We try to show that there is an x in the domain such that f of x equal to y. So let y belong to the codomain. Then as an integer, y could be either greater or equal to 0 or y could be less than 0. As an integer, there are two cases. Y could be either greater or equal to 0 or y could be less than 0. Case 1. If y is greater or equal to 0, then y must be obtained from the first formula. If y is positive, then y must be obtained using the first formula. So if I have y equal to x minus 1 over 2, I multiply both sides by 2. 2y is x minus 1. So my x can be written as 2x minus 1. 2x plus 1. My x can be written as 2y plus 1. If I solve for x, my x can be written as 2y plus 1. So if y is greater or equal to 0, let x equal to 2y plus 1. 2 times a positive integer plus 1 must be a natural number. 2 times a non-negative integer plus 1 is always greater or equal to 1. It must be a natural number. So x belongs to the domain. I find x in the domain. And f of x, then f of x equal to f of 2y plus 1. 2y plus 1 is always the odd number. Since y is an integer, 2 times integer plus 1 is always an odd number. Since it's an odd number, I plug it into the first function. Plug into the first function, I have 2y plus 1 minus 1 over 2. If I simplify, cancel positive 1, negative 1, I get 2y over 2. 2y over 2 is y. So I have when y equal to 0, when y is greater or equal to 0, I find an x such that f of x equal to y. That's case 1. Case 2, if y is less than 0. If y is less than 0, it must be obtained from the second part of the function. If y is less than 0, it must be obtained from the second piece of the function. For the second piece, if I set y equal to negative x over 2, I can multiply both sides by negative 2. So my x is negative 2y. So in case 2, let x equal to negative 2y. Since y is strictly less than 0, something strictly less than 0 multiplied by negative 2 will be strictly greater than 0. So that's an integer. Since y is an integer times negative 2, that's a natural number. Negative number times negative number is positive. So we have a positive integer. Positive integer is a natural number. So s equal to negative 2y is a natural number. Then f of x equal to f of negative 2y. Negative 2y is always an even number. Y is an integer. Negative 2 times integer is even. So since negative 2y is an even number, we plug in negative 2y into the second piece of the function. I have negative 2y over 2. Double negative become positive. I get 2y over 2, which is also y. So when y is less than 0, I can also find x such that f of x equal to y. Since in both cases I can find x and make f of x equal to y, this function f is an onto function. So f is onto. Since f is a one-to-one and onto, it's a bijection. Therefore, f is a bijection. Since there's a bijection from n to z, then they have the same cardinality. Hence, they have the same cardinality. Next, how about the set of natural number and the set of rational number? Do they have the same cardinality? How about the set of natural number and the set of rational number? Do they have the same cardinality? The answer is yes, but the proof is not easy. So if we want to prove it, let me introduce a theorem first. This theorem is called Schroeder-Bernstein theorem. Schroeder-Bernstein theorem. This theorem says if let A and B be two sets, if cardinality of A is less or equal to cardinality of B, and cardinality of B is less or equal to cardinality of A, then they have the same cardinality. Then cardinality of A equal to cardinality of B. In other words, this theorem can be restated as if there exists one-to-one functions if there exists one-to-one functions f from A to B and g from B to A. If there exists one-to-one functions f from A to B and g from B to A, then there exists a bijection from A to B. Or you can also say there is a bijection from B to A. So this is called Schroeder-Bernstein theorem. Let A and B be two sets. If cardinality of A is less than cardinality of B, and cardinality of B is less than cardinality of A, then A and B has the same cardinality. In other words, this theorem can be restated as: if there exists one-to-one functions f from A to B and g from B to A, then there exists a bijection from A to B or from B to A. Now, next, we try to use Schroeder-Bernstein theorem to prove that cardinality of natural number and cardinality of natural number and rational number are the same. Now let's prove it. First of all, we know that the set of natural numbers, they are all rational numbers. The set of natural number is a subset of the set of rational number. So we know, since natural number is a subset of rational number, the cardinality of natural number is less or equal to the cardinality of rational number. That's clear. Next, in order to complete the proof using Schroeder-Bernstein theorem, we try to show that cardinality of rational number is less or equal to the cardinality of natural number. So we want to show that cardinality of rational number is less or equal to the cardinality of natural number, which means we need to show that there's a one-to-one function from the set of rational number to the set of natural number. A rational number can always be written as a fraction of whole number over whole number. A rational number can always be written as a fraction, a whole number over whole number, where A and B are integers and B cannot be 0. That's how we define rational number. But we know for any fraction we can reduce it to the lowest form. For any fraction we can reduce it in lowest form. So also, S can be rewritten as, if I reduce it, it can be written as either positive A over B or negative A over B. Where if I reduce the fraction to the lowest form, A and B must be positive integers. If I reduce a fraction to the lowest form, A and B must be positive integers. And the greatest common divisor of AB must be 1. If I reduce a fraction to the lowest form, it's either positive or negative, where AB must be natural numbers, and the greatest common divisor of AB must be 1. For example, suppose we have a rational number x equal to, for example, 10 over 12. It can be rewritten as positive 5 over 6, where the numerator and denominator, they are both natural numbers, and the GCD of the numerator and denominator is 1. Or if x is 4, I can write it as positive 4 over 1. We have natural number over natural number, and the GCD of these two numbers is 1. If the natural number is negative 5 over negative 15, it can be reduced as positive 1 over 3, and we can see that the GCD of 1 over 3 is 1. Or if x is negative 18 over positive 12, it can be written as negative 3 over 2, where GCD of 3 and 2 is 1. So any rational number can be written in the form of positive negative a over b, where a and b, they are natural numbers, and the GCD of AB is 1. Let's call this form the lowest, simplest fraction form. Let's give a name to this form. Let's call this simplest fraction form. So every fraction, every rational number can be written in the simplest fraction form. Any natural number, any rational number can be written in the simplest fraction form. Now next, I try to find a function. Next, I try to find a one-to-one function from natural number to natural number. Let f from q to n be defined as f of x equal to equal to 1 if x is 0. Let's take 0 as a special case because it's hard to tell 0 is positive or negative. Let's take 0 as a special case. If x is 0, let me assign 0 to 1. F of 0 equal to 1. If x is positive, if it's x positive, then x can be written as a over b in the simplest fraction form. Then I can map this number to 3 to the power a times 5 to the power b. 3 raised to an integer power and 5 raised to an integer power is a natural number. 3 raised to integer power, 5 raised to integer power. 3 raised to integer power, 5 raised to integer power. It's a natural number. And if x is less than 0 and x equal to negative a over b in the simplest fraction form, I can map this number to 2 times 3 to the power a, 5 to the power b, which means I map all positive numbers to some odd numbers. I map all negative numbers to some even numbers. So here, x equal to a over b is in a simplest fraction form, where x equal to a over b or x equal to negative a over b is, they are in the simplest form, simplest fraction form. we can see that here 3 raised to integer power times 5, 3 raised to positive integer power and 5 raised to positive integer power must be a natural number. Since a and b, they are natural numbers, 3 raised to positive integer power times 5 raised to positive integer power must be a positive integer, which is a natural number. And same thing here, 2 times 3 to the power 2 times 3 to the power a and 5 times 3 to the power b. Since a and b, they are positive integers, this is a natural number. So f is a function from rational number to natural number. Next, we try to show that this function is a one-to-one function. In order to show f is a one-to-one function, let me first of all show you some example about how this function works. For f of 0, 0 is a rational number. If I plug in 0, if s is 0, when s is 0, f of x is 1. So f of 0 is 1. That's a special case. Another example, how about f of 4? How about f of 4? 4 is a rational number. If I plug in 4, I first of all rewrite 4 as a simple fraction. So 4 can be rewritten as 4 over 1. This is a positive number. I plug in 4 for a, plug in 1 for b in the first pieces of the function. Since 4 is a positive number, I plug in 4 and 1 into the first piece of the function. I get 3 to the power 4 times 5 to the power 1. And this is a natural number. 3 raised to power 4 times 5 raised to power 1, this is a natural number. So f assign a rational number to a natural number. Another example, how about f of negative 6? First of all, we rewrite negative 6 in a simple fraction form. This can be rewritten as negative 6 over 1. And negative 6 is less than 0. So when we plug into the function, I plug in 6 over 1 into the last piece of the function. I have 2 times 3 to the power 6, 5 to the power 1. I plug in 6 for a, plug in 1 for b. So f assign a rational number to a natural number. Another example, f of a over 6. A over 6 is not in a simple fraction form. A over 6 is not in a simple fraction form. So first of all, I rewrite a over 6 as a simple fraction. A over 6 can be rewritten as 4 over 3. And since a over 6 is greater than 0, I plug in 4 over 3 into the first piece of the function. I have 3 to the 4 times 5 to the power of 3. I plug in 4 for a, plug in 3 for b. How about f of 4 over negative 12? F of 4 over negative 12, this is not in the simplest form. So I rewrite this fraction in the simplest form. I have f of negative 1 over 3. This is a fraction in the simplest form. Since this number is less than 0, I use the third piece of the function. I have 2 times 3 to the power 1, 5 to the power of 3. I plug in 1 for a, plug in 3 for b. Next, how about f of negative 14 over negative 12? For f of negative 14 over negative 12, we first of all rewrite negative 14 over negative 12 in the simplest fraction form. It can be rewritten as 7 over 6. So 7 over 6 is greater than 0. We use the first piece of the function. I plug in 7 for a, plug in 6 for b. I have 3 to the 7 times 5 to the 6. Another example. How about f of 1.8? 1.8, if I write it in a simplest fraction form, it can be rewrite as 18 over 10. First of all, rewrite it as a fraction, 18 over 10. Then 18 over 10 can be reduced as 9 over 5. That's in a simplest fraction form. And this number is greater than 0. I plug in into the first piece of the function. I plug in 9 for letter A, plug in 5 for letter B. I plug in 9 for letter A, plug in 5 for letter B. How about f of negative 3.5? I first of all rewrite negative 3.5 in the simplest fraction form. It can be rewrite as negative 7 over 2. First of all, you can write it as negative 35 over 10. And 35 over 10 can be reduced as 7 over 2. This number is less than 0. This number is less than 0. So we apply the third piece of the function. We have 2 times 3 to the power 7 times 5 to the power of 2. So that's how we assign rational number to natural numbers using this function f. Next, I'll show you f is a one-to-one function. In order to show f is a one-to-one function, I first of all let s1, s2 belong to the domain. Let s1, s2 belong to the domain. Assume f of s1 equal to f of s2. Then there are 3 cases. Case 1, f of s1 equal to f of s2 equal to 1. F of s could be 1. That's first case. Case 2, f of s1 equal to f of s2. In the first case, 3 to the power a times 5 to the power b must be an odd number. So second case, f of x could be odd. It could be odd number other than 1. Case 2, f of s1, f of s2, it could be odd number other than 1. Case 3, in the third case, f of x could be even number. 2 times any number is even. So case 3, f of s1 equal to f of s2, it could be an even number. So there are 3 cases. Let's discuss each cases individually. Case 1. If f of s1 equal to f of s2 equal to 1, the only possibility is that s equal to 0. If f of x equal to 1, the only possibility is that s equal to 0. So s1 equal to 0, x2 equal to 0, then we have x1 equal to s2 since they are both equal to 0. s1 equal to s2, that's case 1. Case 2. If f of s1 equal to f of s2 is an odd number other than 1, if f of s1 equal to f of s2 is an odd number other than 1, then both s1 and s2 must be greater than 0. Then both x1 and x2 must be greater than 0. If f of s1 equal to f of s2 is an odd number other than 1, then both x1 and x2 must be greater than 0. So in their simplest form, in their simplest fraction form, S1 can be written as A1 over B1, and X2 can be written as A2 over B2. Therefore, f of S1 is 3 to the power of A1 times 5 to the power of B1, and f of S2 is 3 to the power of A2 times 5 to the power of B2. Then, by unique prime factorization theorem, every integer greater than 1 can be written as a product of prime in a unique way. 3 to the power of A1, 5 to the power of B1, and 3 to the power of A2, 5 to the power of B2, they are integers greater than 1. Since A and B are greater or equal to 1, they are integers greater than 1. And 3 and 5, they are both primes. So these two numbers can be written as a product of prime number in a unique way. That means if they are the same, the exponent must be the same. So by unique prime factorization theorem, A1 equal to A2 and B1 equal to B2. Since A1 equal to B1, A1 equal to A2, B1 equal to B2, then x1 must equal to s2. Since the numerator is the same, denominator is the same, x1 must equal to s2. So in case 2, we also have s1 equal to s2. Case 3. F of s1 equal to f of s2 is an even number. If f of s1 is equal to f of s2 is even, it must be in the third case. It must be, in this case, 2 times 3 to the power of a times 4 to the power of b. So both s1 and s2 must be less than 0. Then both s1 and s2 must be less than 0. Since they are less than 0, in their simple fraction form, S1 can be written as A1 or negative A1 over B1. And S2 equal to negative A2 over B2. Then if I plug in S1, S2 into the function, I have 2 times 3 to the power of A1 times 5 to the power of 8 B1. If I plug in S2, I have 2 times 3 to the A2 times 5 to the power of B2. Since f of S1 equal to f of S2, when I plug in S1, I get answer the same as when I plug in S2. So when I plug in S1, S2, that's what I get. When I plug in S1, I get this. When I plug in S2, I get this. Then again, by unique prime factorization theorem, this is a number greater than 1. This is an integer greater than 1. This is also integer greater than 1. By unique prime factorization theorem, every integer greater than 1 can be written as a product of prime number in a unique way. And they are all primes. 2, 3, and 4, and they are all primes. That means their power, their exponent must be exactly the same. For number 2, exponent is 1, it match. For number 3, exponent A1, A2 must be the same. For number 5, exponent b1, b2 must be the same. Since a1 equal to a2, b1 equal to b2, that means numerator must be the same as numerator, denominator must be the same as denominator. So we have x1 equal to x2. Since in all three cases we have s1 equal to s2, then we know that f is 1 to 1. Therefore, f is 1 to 1. So, since f is 1 to 1, we know that cardinality of q must be less than cardinality of n. Cardinality of q must be less than or equal to cardinality of n. Since cardinality of n is less or equal to cardinality of q, and cardinality of q is less or equal to cardinality of n, then by Schroeder-Bernstein theorem, by Schroeder-Bernstein theorem, cardinality of n equal to cardinality of q. Since cardinality of n is less than or equal to cardinality of q, and cardinality of q is less or equal to cardinality of n, then by Schroeder-Bernstein theorem, cardinality of n equal to cardinality of q. Next, let me introduce countable sets. Let S be a set. We say S is countable. If S is finite, or cardinality of S is the same as the cardinality of natural number. If S is not countable, then we say S is uncountable. If S is not a countable set, then we say S is uncountable. If S is finite, or cardinality of S is the same as cardinality of natural number, then we say S is countable. If S is not a countable set, then we say S is uncountable. So from the previous example, we know that cardinality of natural number is the same as cardinality of integers, and it's the same as cardinality of rational numbers. Then we know that the set of integer, the set of rational number, they are all countable. Then we know the set of integers, the set of rational numbers, they are countable. Since they have same cardinality as natural number, then we say they are both countable. Now, how about real number? How about real number? Is real number countable? Is the set of real number countable? This question is hard to answer. It's hard to answer right now. Let me introduce some simple concept first. For real numbers. Note, every real number has a unique decimal representation. Infinite decimal representation. If we exclude the form with a tail of 9s, what does it mean? Every real number has a unique infinite decimal representation. If we exclude the form with a tail of 9s, what does it mean? Let me show you some example. First of all, a real number has a unique decimal representation. It looks like this. For example, 1/3 is a real number. It can be written as 0.33333 and so on. That's called infinite decimal representation. 1/2 is 0.5. 1/2 is 0.5. It can be written as 0.50000 and so on, with infinitely many zeros. That's called an infinite decimal representation. And we know pi is a real number. It has 3.14159265535 and so on. That's called infinite decimal representation. Square root of 2 is 1.414 and so on. E is 2.718 and so on. So every real number has infinite decimal representation. Every real number has a unique infinite decimal representation. It can be written as in a unique way. It can be written in the decimal representation in a unique way. And what does it mean? So if we exclude the form with a tail of 9s, what does it mean? A tail of 9s. A tail of 9. Look at your example. 2.49999. If a decimal number ends infinitely many 9s, that's called a tail of 9s. If in calculus class, we'd actually take a limit for this number. In calculus class, we actually take a limit for this number. This number can be rewritten in a better way. So if I let x equal to 2.49999, then how about 10x? 10x can be rewritten as 24.9999. Then what's 10x minus x? For 10x minus x, you use 24.9999 minus 2.49999. 24.99999 minus 2.4999999. And when we subtract, infinitely many 9 get cancelled. 9 minus 4 is 5. 24 minus 2 is 22. I get 22. Sorry, 9 minus 4 is 5. I get 22.5. So 10x minus x is 22.5. And if I combine like term here, 10x take away x is 9x. Then if I divide both sides by 9, x is 2.5. So 2.49999 is the same as 2.5. It's the same as 2.50000. That's what we know from calculus class. That means any terminate decimal number, any finite decimal number, or any terminate decimal number has two representations. Any finite decimal number has two representations. So to make it unique, we exclude this form. To make decimal representation unique, we exclude this form. We write 2.5 as 2.5000. If I exclude this form, every real number has a unique infinite decimal representation. If I exclude this form, then 2.5 can only be written as 2.50000. So every real number has a unique infinite decimal representation if we exclude the form with a tail of 9s. Now, is the set of real number countable? To answer this question may be too hard right now. Let's look at a simpler version first. Is the interval from 0 to 1 countable? Is the interval from 0 to 1 countable? The answer is no. The answer is no. Let's try to prove it. To directly prove an interval, a set is uncountable is not easy. To prove a set is uncountable is not easy. So let's try to prove by contradiction. To prove a set is uncountable directly is not easy. So let's try to prove by contradiction. So let's try to show that the interval from 0 to 1 is uncountable. Proof by contradiction. So we assume the interval from 0 to 1 is countable. Assume the interval from 0 to 1 is countable. Since this is not a finite set, then its cardinality must be the same as natural number. A countable set must either be finite or has the same cardinality as natural number. Since this interval is not finite, there are infinitely many numbers in the interval. This set is not finite, so it must have the same cardinality as the natural number. Since it's countable, it must have the same cardinality as the natural number. If two sets has the same cardinality, then there is a bijection between two sets. By definition of cardinality, if two sets have the same cardinality, then there is a bijection between two sets. So there exists a bijection f from n to the interval 0, 1, from natural number to the interval 0, 1. Bijection means 1 to 1 and on 2. So f of 1, f assign 1 to some number between 0 and 1. I don't know what it is. Let's call y of 1. Y sub 1 is a number between 0 and 1. So it can be written as point d11, d12, d13, and d1n, That's a decimal number between 0 and 1. Decimal point, first digit, second digit, third digit. Every real number has a unique decimal representation. Every real number has a unique decimal representation if we exclude the tail of 9s. F of 2 equal to some number between 0 and 1 that has a different representation called D21, D22, D23, D21, D22 then represent digits between 0 and 9. That's called decimal representation. And F3 is y sub 3 equal to D31, D32, D33, D3n. And in general, f of n is y sub n. It's dn1, dn2, dn3, dnn, and so on. This is an infinite set. So f assign every natural number to a decimal number between 0 and 1, where dij, each dij represents a decimal number, represent a number between 0 and 9. Where dij represent digits 1, 2, 3, 4, 5, 7, 8, 9. And we exclude the form with a tail of 9s. If it has a tail of 9, we can write it as a finite decimal number, then written as a number with a tail of zeros. So let me first of all show you an example about what I mean here. So for example, if f of 1 equal to some number between 0 and 1, for example, if my y1 is 2 over 7, then 2 over 7 is 0.285714, 285714. I call my first digit D11, so my D11 is 2. I call my second digit D12, my D12 is 8. I call my third digit my D13, my fourth digit my D14. So here my D11 is 2, my D12 is 8, my D13 is 5, my D14 is 7. Each dij is a number between 0 and 9. And 7 over 2 is my y1. That's an example. Another example, for example, if my f of 2, say, is a half, just for example, then a half will be my y2. A half will be my y2. Half can be written as 0.50000, and so on. So this is my D21. My D21 is 5. My D22 is 0. D23 is 0. D24 is 0. And so on. So that's what I mean here. F of 1 is a number between 0 and 1. F of 2 is a number between 0 and 1. Every number is a number between 0 and 1 here. So the range of f the range of f of n is the set of all these y's. The set of all possible outcomes is a range. So the range is the set of all possible outcomes. It's the set of y's. y1, y2, y3 up to yn. y1, y2, yn, and go to infinity. There are infinitely many numbers. That's my range. Since f is a bijection, it must be both 1 to 1 and on 2. In order to find a contradiction, next I try to show f is not on 2. In order to find a contradiction, next I try to show f is not on 2. So if I want to show a function is not on 2, I try to find an element in a codomain, but not in the range. Next, in order to show f is not on 2, I try to find an element in the codomain, but not in the range. So next, I try to find an element in the codomain, but not in the range. Let y equal to point d1, d2, d3, d4, and so on, where di has two possible outcomes. Di is 0 if d11 is odd. Di is 1 if d11 is dii. D1 is 0 if dii is odd. D1 equal to 1 if dii is even. Then since di could be either 0 or 1, then y is a decimal number between 0 and 1. I start from decimal point here, point d1, d2, d3. Since di is either 0 or 1, y is a number between 0 and 1. So y belongs to 0 and 1. Let me use an example to show you how my y looks like. I think it will make more sense to you. So go back to the previous example here. My f of 1 is 2 over 7, f of 2 is 1 over 2. That's my d11, d12. If I continue, I assume my f of 3, for example, f of 3 equal to some number between 0 and 1. For example, if my f of 3 is 1/3, that's my y3. One-third in decimal form is 0.33333. So that's my d31. My d31 is 3. My d32 is 3. My d33 is 3. My d34 is 3. F of 4. Pick another number between 0 and 1. Say my f of 4 is, for example, 5 over 9. 5 over 9 is 0.55555 and so on. So that's my d. 5 over 9 is my y4. First 5 is my d41. Second 5 is my d42. The third 5 is d43. My fourth one is d44, and so on. Now how do I pick my y's? How do I pick my y? How do I pick my d1, d2, d3, d4? So for d1, look at d11. For d1, I look at d11. My d11 is 2. If my d11 is even, I pick my d1 to be 1. Now for d22, look at my d22. Since my d22 is 0, 0 is even, I pick my d22 to be 1. Since my d22 is even, I pick my d2 to be 1. And next, my d33. d3 depends on my d33. My d33 is 3. 3 is odd. So I take my D3 to be 0. If dii is odd, my di is 0. Next, my D44. D44 is 5, which is odd. D44 is 5, which is odd. So I take my D4 to be 0. If D11 is even, I pick my D1 to be 1. If my D22 is even, I pick my D2 to be 1. If my D33 is odd, I pick my D3 to be 0. If my D44 is odd, I pick my D4 to be 0. So my y will be 0.1100 and so on. You can see that my first digit won't be the same as D11. My second digit won't be the same as D22. My third digit won't be the same as D33. My fourth digit won't be the same as D44, and so on. So my di is 0 if my dii is odd. My di is 1 if my dii is even, where I equal to 1, 2, 3, and so on. I could be any integers. So y is a number between 0 and 1. And we know that my d1 doesn't equal to d11. My d2 doesn't equal to d22. d3 doesn't equal to d33, and dn doesn't equal to dnn. Since d1 doesn't equal to d11, d2 doesn't equal to d22, and in general dn doesn't equal to dnn. And we know that for all these representation, we exclude the form of a tail of 9s. That means every representation for y1, y2, y3 are unique. Every decimal representation here are unique. Since I exclude the tail of 9s, all representation here is unique. If d1 doesn't equal to d11, if d1 doesn't equal to d11, if the first digit doesn't match, then y doesn't equal to y1. If the first digit doesn't match, then y doesn't equal to y1. If d2 doesn't equal to d22, that means the second digit doesn't match. So y doesn't equal to y2. And in general, y doesn't equal to yn. If y doesn't equal to any of these elements, then if y doesn't equal to any of these elements in the set, then we know y doesn't belong to the set. Since y doesn't equal to any elements in the set, then y doesn't belong to the set. And we know that y is a number between the codomain. Y is an element in the codomain, but y is not in the range. So we know f is not onto. Since we assume f is a bijection, but we show that f is not onto, it's a contradiction. If we find a contradiction, that means the initial assumption was wrong. So the interval 0 to 1 must be uncountable. If this assumption is wrong, the interval from 0 to 1 must be uncountable. Therefore, the interval from 0 to 1 must be uncountable. Next example. Is it true that cardinality of this interval 0, 1 is the same as the cardinality of the interval 0, 1? including 0. Are they the same? We know that they both have cardinality infinity, but this set has one extra element. Do they have the same cardinality? The answer is yes. Let's prove it. The answer is yes. Let's prove it. If we try to show two sets has the same cardinality, we must show that there is a bijection between two sets. If we want to show two sets has the same cardinality, we need to show that there's a bijection between two sets. So let f be a function from the interval 0, 1 to the interval 0, 1, including 0. We try to find a function from first interval, from first set to the second set, and that's bijection. How do we find a function? Let me show you the construction for the function here. That's the interval from 0 to 1. 0 to 1 represents all decimal numbers between 0 and 1. So a half is a number between 0 and 1. 1 over 4 is a number between 0 and 1. 1 over 8 is a number between 0 and 1. All numbers in the form of 1 over 2 to the power n is between 0 and 1. And let me put all the numbers in the form of 1 over 2 to the power n together, and the numbers not in the form of 1 over 2 to the power n together. So that's a subset of this interval. That's another subset of this interval. Together, I get the entire interval from 0 to 1. And the other set, interval from 0 to 1, including 0, everything is the same, but it has an extra element 0. Everything is the same, it has an extra element 0. Now, next, I try to find a function that assign each element in the first set into the second set, and that's a bijection. I can first of all assign a half to 0. Then I assign 1 over 4 to a half. I assign 1 over 8 to 1 over 4. Assign 1 over 16 to 1 over 8. Assign 1 over 32 to 1 over 16. So if I keep this process, the entire list here will be assigned to this list here, and including an extra 0. Next, for numbers not in the form of 1 over 2 to the power n, I assign each number to itself. For example, 1 over square root of 2, that's not in the form of 1 over 2 to the power n, where n must be whole numbers. N must be whole numbers. Since n must be whole numbers. So 1 over square root of 2 is not in the form of 1 over 2 to the power n. I assign each number to itself. And 4 over 7 is not in the form of 1 over 2 to the power n. I assign the number to itself. So same thing, I assign every number that is not in the form of 1 over 2 to the power n to number itself, I assign every number that's not in the form of 1 over 2 to the power n to itself. So you can see that this is a one-to-one mapping. This is a one-to-one. I didn't assign any element to the same element. I didn't assign any two elements to the same element. This is a one-to-one mapping. This is a one-to-one assignment. And also, this is onto. Every element in the second set has an inverse image. This is onto. Every element in the second set here has an inverse image. This is onto. This is onto. So, how do I write f of x? The f from the interval 0, 1 to the interval 0, 1, including 0, be defined as f of x first of all assign a half to 0. So f of x equal to 0 if x equal to a half. I first of all assign half to 0. Next, I assign a quarter to a half, 1/8 to a quarter, 1/16 to 1/8. It looks like 1/4 times 2 is half. 1/8 times 2 is 1/4. It looks like I multiply each number by 2. I multiply each number by 2. So next, for 1/4, 1/8, 1/16, I multiply by 2. For 1/4, 1/8, 1/16, I multiply number by 2. If x is in the form of 1/2 to the power n, where n equal to 2, 3, 4. Start from 1/4. I take 1/4 multiplied by 2, I get 1/2. Take 1/8 multiplied by 2, I get 1/4. So 1/4 is 2 is n. 1/2 is 2 raised to power 2. So n starts from 2. 1/8 is 2 raised to power 3. 1/16 is 2 raised to power 4. So n equal to 2, 3, 4, and so on. That's the rest of the list. Here I assign the rest of the list. For the rest of the list, I multiply each number by 2. I get half, a quarter, 1/8, 1/16, and so on. Next, for the other numbers, if x is not in the form of 1/2 to the power n, where n equal to 1, 2, 3, 4. If x is not in the form, I assign every number to itself. That means I assign x to x. I assign every number to itself. So I assign f of x to x. So this is a bijection. Next, let's prove it. First of all, let me show that f is 1 to 1. So let x1, x2 belong to the domain. Assume f of s1 equal to f of s2. We try to show that s1 actually equal to s2. If f of s1 equal to f of s2, then we have 3 cases. There are 3 cases. In the range, there are 3 cases. F of s1, s2 could be either 0, could be 1/2 to the power n, or could be not in the form of 1/2 to the power n. There are 3 cases. So there are 3 cases. Then we have 3 cases here. Case 1. F of s1 equal to f of s2 equal to 0. Case 2. F of s1 equal to f of s2 is in the form of 1/2 to the power n, where n is an integer 1, 2, 3, 4, 5, equal to 1/2 to the power n equal to 1, 2, 3, and so on. Case 3. Case 3. They are not in the form of 1/2 to the power n. Case 3. They are not in the form of 1/2 to the power n. F of s1 equal to f of s2, but they are not in the form of 1/2 to the power n, where n equal to 1, 2, 3, and so on. So there are 3 cases. Case 1. Let's deal with each case individually. Case 1. F of s1 equal to f of s2 equal to 0. If f of s1 equal to f of s2 equal to 0, it must be obtained from the first case. If f of s1 equal to f of s2 equal to 0, it must be obtained from the first case. Then, in the first case, both s1 and s2 must be a half. Then s1 equal to a half, and s2 equal to half. So we have s1 equal to s2. That's case 1. Case 2. If f of s1 equal to f of s2, That's in the form of 1 over 2 to the power n equal to 1, 2, 3, and so on. Then it must be obtained from case 2. They must be obtained from case 2. If f of x is in this form, they must be obtained from the second form. So I substitute x1, substitute x2, I have 2s1 equal to 2s2. Then if I divide both sides by 2, I have x1 equal to s2. That's case 2. Case 3, if f of s1 equal to f of s2, and they are not in the form of 1 over 2 to the power n, where n equal to 1, 2, 3, and so on. If f of x1, f of s2 is not in the form of 1 over 2 to the power n, then they must be obtained from the third form. F of s1, s2 must be obtained from the third form. In the third form, f of x equal to x, so f of s1 equal to x1, and f of s2 equal to x2. In the third form, f of x equal to x. If I plug in s1, I get s1. If I plug in s2, I get s2. So in all three cases, we get the same conclusion. Then f must be 1 to 1. So f is 1 to 1. Next, I try to show f is on 2. So I let y belong to the codomain. Pick element y from the codomain. I try to show that there is x in the domain such that f of x equal to y. So if I let y belong to the codomain, again, there are three cases. If y belongs to the codomain, there are three cases. Y could be either 0, it could be in the form of 1 over 2 to the power n, or it could be not in the form of 1 over 2 to the power n. There are three cases. Y could be either 0, it could be in the form of 1 over 2 to the power n, or it could be not in the form of 1 over 2 to the power n. There are three cases. So there are three cases. Case 1, y equal to 0. Case 2, y equal to 1 over 2 to the power n, where n equal to 1, 2, 3, and so on. Case 3, y is not in the form of 1 over 2 to the power n, where n equal to 1, 2, 3, and so on. There are three cases. Case 1. Case 1. If y is 0, then x must be a half. If y is 0, I let x equal to half, f of x will be y. If y is 0, I let x equal to half, f of x equal to y. So if y is 0, let x equal to a half, which belongs to the domain. Then f of x equal to f of a half. F of half is 0, which equal to y. So that's case 1. Case 2. Y is in the form of 1 over 2 to the power n, where n equal to 1, 2, 3, and so on. If y is in the form of 1 over 2 to the power n, we can try to obtain x from the second formula. If y is in the form of 1 over 2 to the power n, we can try to find x from the second formula. So in the second formula, y is 2x. If I divide both sides by 2, I have y, half of y equal to x. If I divide both sides by 2, I have half of y equal to x. So if y is in the form of 1 over 2 to the power n, I have 1 over 2 times 1 over 2 to the power n. So my x is 1 over 2 to the power n plus 1. Since each n is 1, 2, 3, 4, n plus 1 will be 2, 3, 4, 5. So x is in the form of 1 over 2 to the power n equal to 2, 3, 4, and so on. Since each n is 1, 2, 3, 4, 5, then n plus 1 could be 2, 3, 4. n plus 1 will be 2, 3, 4. So s equal to 1 over 2 to the power n, where each n here is 2, 3, 4, 5. So let x equal to half of y. Then s equal to 1 over 2 to the n plus 1. Then x equal to 1 over 2 to the power n, where each n is 2, 3, 4, and so on. And this n belongs to the domain. This n belongs to the domain. If I plug in 2, I get 1 over 4. That's in the domain. Plug in 3, I get 1 over a. That's in the domain. So this x belongs to the domain. And this x satisfies the second condition. I can use the second formula to find y. I can use the second formula to find y. So in this case, my f of x satisfies the second condition. I have f of half of y. That satisfies the second equation. So I have 2 times half of y. 2 times half of y is y. So in the second case, I also find x such that f of x equal to y. Case 3. If y not equal to 1 over 2 to the power n, for n equal to 1, 2, 3, and so on, we can try to find x from the third piece of the function. I can try to find x from the third piece of the function. In this case, I simply let y equal to x. In the last piece, y equal to x, so s equal to y. Let s equal to y. Since y is not in this form, then we know y is between 0 and 1. We know this y is not 0, so it's between 0 and 1. We take care of the case that y equals 0 already, so in this case y is not 0. If y is not 0, it belongs to the domain 0 to 1. So f of x equal to f of y. Since y is not in the form of 1 over 2 to the power n, we need to apply the last case that equal to y. So f of x equal to y. In all three cases, we show that f of x equal to y. So therefore, f is onto. Since f is 1 to 1 and onto, therefore it's a bijection. Since I find a bijection between two sets, these two sets has the same cardinality. Next example. Is it true that cardinality of this interval 0 to 1 is the same as the cardinality of the closed interval from 0 to 1? Is it true that they have the same cardinality? Again, the answer is yes. Let's prove it. To prove two sets has the same cardinality, we need to find a bijection between two sets. So let f be a function from the open interval 0, 1 to the closed interval 0, 1. How do we find a bijection between two functions? Let's look at the previous example, the old example first. In the old example, we found a bijection from open interval 0, 1 to interval 0, 1, including 0. Now, if I include 1, if I use closed interval here, I include 1. If I include 1, there's an extra element 1 in the set. If I include 1, now we have two extra elements in the set. We have 0 and 1. If I include 0 and 1, now I have two extra elements, 0 and 1 in the set. How do I find a bijection between these two functions? Let me show you the idea here. I can find a function. I can find a function assign a half to 0. I assign half to 0. I assign a quarter to 1. I assign 1 over a to a half. I assign 1 over 16 to a quarter. I assign 1 over 32 to 1 over a. The next one, I assign 1 over 64 to 1 over 16. Then, if I keep this assignment, the entire list will be assigned. The entire list will be assigned by some numbers from the first list. Next, for the numbers not in the form of 1 over 2 to the power n, again, I assign a number to the number itself. For the number not in the form of 1 over 2 to the power n, I assign each number to itself. For the number not in the form of 1 over 2 to the power n, I assign each number to itself. Because these two sets is the same in both intervals. These two sets is the same. The only difference in this set, we have two extra elements, 0 and 1. And this sequence here take care of every element in this sequence here. Next, how we run the function f? How do we run the function f? Based on this assignment, how do we run the function f? Let f be a function from the open interval 0, 1 to the closed interval 0, 1, be defined as f of x. F of x assign a half to 0. So f of x is 0 if x equal to a half. F of x equal to 1. I assign a quarter to 1. F of x equal to 1 if x equal to a quarter. For the rest, I assign 1 over a to a half, 1 over 16 to a quarter. It looks like 1 over a times 4 is a half. 1 over 16 times 4 is a quarter. 1 over 32 times 4 is 1 over a. So for the rest, if x is in the form of 1 over 2 to the power n, I start from 1 over a. So n must be 3, 4, 5, and so on. Since I start from 1 over a, 1 over a is 2 to the power 3. 1 over 16 is 2 to the power 4. So n start from 3, 4, 5, and so on. Here I multiply 1 over a by 4, I get a half. I multiply 1 over 16 by 4, I get 1 over 4. So for each element here, I multiply by 4, equal to 4x if x is in the form of 1 over 2 to the power n, where n equal to 3, 4, 5. And the rest, I assign the number to itself. For the rest, I assign a number not in the form of 1 over 2 to the power n. I assign each number to itself. So I assign x to x. I assign each number to itself. So if x is not in the form of 1 over 2 to the power n, for n equal to 1, 2, 3, and so on, I assign x to itself. So this is a function. If we look at the picture, we can see that it's a bijection. We assign every element to a different element in the codomain. And every element in the codomain has an inverse image. So this is a bijection. Verify that F is a bijection. It's very similar to the previous problem. Verify by yourself. Verify that F is a bijection. It's very similar to the previous example. Since F is a bijection, cardinality of an open interval 0, 1 equal to the cardinality of the closed interval 0, 1. Next example, let A and B be real numbers. Show that cardinality of the interval 0, 1 is the same as the cardinality of the interval A, B. If we want to show that two sets has the same cardinality, we try to show that there is a bijection between two sets. How do we find a bijection between two sets? 0, 1. Interval 0, 1 is somewhere in the number line. 0, 1, 2, 3. That's the interval 0, 1. Interval A, B. A and B could be any integers, could be any real numbers. Can we find a bijection between these two sets? I can try to find a bijection that map, that assign 0 to A, assign 1 to B, and a number in the middle to a number in the middle. Can we find such function that map, that assign 0 to A, assign 1 to B, and number in the middle to the number in the middle? Let's try. Can we find a function that assign 0 to 1, 0 to A, that assign 1 to B? Can we find such function? Can we find a function that assign 0 to A, assign 1 to B? Can we find such function? The number in the middle of 0 and 1 to the number in the middle of AB. Can we find such function? We can think of a straight line passing through 0A and 1B. If we think of this straight line, the slope of the line is right over long. Right is B minus A. Long is 1 minus 0. Slope is right over long. So slope is B minus A. And for this line, the y-intercept is A. So equation of the line can be written as y equal to mx plus b. ms plus b. Slope is b minus a. Y-intercept is a. So this is the function for this line. So that's our scratch work. Let f from the interval 0, 1 to the interval a, b be defined as f of x equal to b minus a times x plus a for x between 0 and 1, not including 0 and 1. Next, we need to show that this function f is a bijection. It's 1 to 1 and onto. So first of all, let's try to show that this function f is 1 to 1. Let S1, S2 belong to the domain 0, 1. Let S1, S2 belong to the domain 0, 1. We assume f of S1 equal to f of S2. Then we try to show that x1 actually equal to s2. Assume f of s1 equal to f of s2. I can substitute s1 for x, then substitute x2 for x. I have b minus a times s1 plus a, and I have b minus a times s2 plus a. I can first of all subtract a from both sides. I have b minus a times s1 equal to b minus a times x2. Here I miss one thing here. In order to have an interval, that a and b cannot be the same. In order to have an interval, a and b cannot be the same. So assume a, b are integers, are real numbers, and a is less than b. Sorry about that. To make in order to have an interval, a, b cannot be the same. So let's assume a is less than b. Then since a is less than b, a and b they are not the same. So b minus a is not 0. I can divide both sides by a non-zero number. I have s1 equal to s2. I divide both sides by b minus a. So I have s1 equal to s2. Next, so f is 1 to 1. Next, I try to show that f is onto. To show f is onto, let y, we pick y from the codomain. Let y belong to the codomain. We try to find an x in the domain. We try to find x in the domain such that f of x equal to y. How do we find x? We can try to find x from here. We can try to find x from here. In order to get x by itself, I can subtract a from both sides, then divide by b minus a. I can subtract a from both sides, then divide both sides by b minus a. So let y belong to interval a minus b, then let b equal to, sorry, let x equal to y minus a over b minus a. I can get x from here. Subtract a from both sides, then divide both sides by b minus a. So I let x equal to y minus a over b minus a. Is this number in the domain? We need to verify, is this x in the domain or not? Is this x in the domain? Since y is between a and b, since y is somewhere between a and b, y minus a, the distance from y to a, must be less than the distance from b to a. So y minus a must be less than b minus a. So y minus a must be less than b minus a. Since y is on the right side of a, y minus a is positive. Since y is greater than a, y minus a is positive. So y minus a is greater than 0, but it's less than b minus a. Y is in the middle of a and b, so y minus a is less than b minus a. For this inequality, if I divide the middle by b minus a, I need to divide the left side by b minus a, divide the right side by b minus a. So y minus a over b minus a is greater than 0, greater than 1. When we divide inequality by a positive number, the direction of inequality stays the same. Since a is less than b, b minus a is positive. So when we divide inequality by negative number, by positive number, the direction stays the same. So y minus a over b minus a is between 0 and 1. So this x is between 0 and 1. This x is between 0 and 1. So x is between 0 and 1. And f of x equal to f of y minus a over b minus a. F of x equal to f of y minus a over b minus a. I plug in this expression for x. I plug in this expression for x. If I plug in, I have b minus a times y minus a over b minus a plus a. I can first of all cancel the denominator. I get y minus a plus a. Then I can cancel positive a, negative a. I get y by itself. So let y equal to, if y is between a and b, let x equal to y minus a over b minus a, then f of x equal to y. So since for y in the codomain, I can find an x in the domain, then f is on 2. Since for all y in the codomain, I can find an x in the domain such that f of x equal to y, then f is on 2. Since f is on 2, since f is 1 to 1 and on 2, this function f is a bijection. Therefore, f is a bijection. Since there's a bijection from the set from the interval 0, 1 to the interval a, b, then they have the same cardinality. Hence, the interval 0, 1 and the interval a, b have the same cardinality. Next example. Show that the interval from -1 to 1 and the interval from -infinity to infinity have the same cardinality. If we try to show that two intervals has the same cardinality, we must show that there is a bijection between two sets. There are more than one way to find a bijection. You can pause the video, find a bijection by yourself. There are more than one way to find an answer. You may not get the same answer as I get. You may have a different answer. There are more than one way to find an answer. Let me show you my answer here. Let f from -1 to 1 to -infinity to infinity. Let function f be defined as f of x equal to 1 equal to x over 1 plus x. If x is between -1 and 0, let f of x equal to x over 1 minus x if x is between 0 and 1, including 0. Next, let's prove this function f is a bijection. Next, let's prove that this function f is a bijection. First of all, let's try to show that f is 1 to 1. Let x1, s2 belong to the domain. Assume f of s1 equal to f of s2. Assume f of s1 equal to f of s2. Then we try to show that x1 equal to s2. If I can prove that s1 equal to s2, then the function is 1 to 1. How do we show that s1 equal to s2? This is a piecewise function. Let's consider different cases. In the first case, x is between -1 and 0. If x is between -1 and 0, then x plus 1 will be positive number. If x is between -1 and 0, then 1 plus x will be positive number. X by itself is negative. Negative over positive is negative. So the first piece of the function is negative. Look at the second piece. x is between 0 and 1. If I plug in number between 0 and 1, 1 minus a number between 0 and 1 is positive. X by itself is positive. Positive number over positive number is positive. So f of s could be either positive or negative. Same thing, since f of s1 equal to f of s2, they may be both positive or both negative. So here we have two cases. Case 1, f of s1 equal to f of s2, they may be both positive. Case 2, they may be both negative. The reason I include 0 in the first case is because if I substitute 0, I get 0. So f of s1, f of s2 could be 0. Now, case 1. If f of s1 equal to f of s2, that's greater or equal to 0, then they must be obtained from the second piece. Second piece is positive. If f of s1 equal to f of s2, that's greater or equal to 0, both functions must be obtained from the second piece of the function. Since both functions are obtained from the second piece of the function, then both s1 and s2 must be between 0 and 1. Then we know that x1 and x2 must be between 0 and 1. So I plug in x1, x2 into the second piece of the function. So I have s1 over 1 minus s1 equal to x2 over 1 minus x2. Next, I try to show that s1 equal to s2. How do we show s1 equal to s2? For equation, I can try to cross multiply. I have s1 times 1 minus s2 equal to s2 times 1 minus s1. Then distribute s1 minus x1 s2 equal to s2 minus s1 s2. I can add minus s1 s2 to both sides. Add x1 s2 to both sides. They get cancelled. So I have s1 equal to s2. That's case 1. Case 2. If f of s1 equal to f of s2 is less than 0. If f of s1 equal to f of s2 is less than 0, then they must be obtained from the first piece of the function, because first piece of the function is negative, second piece is positive. So both of them must be obtained from the second piece of the function. So both s1 and s2 must be between -1 and 0. Then s1 and s2 must be between -1 and 0. So I plug in s1, s2 into the first piece of the function. So I have x1 over 1 plus x1 equal to x2 over 1 plus x2. Since s1, s2 cannot be -1, so denominator is not 0, I can cross multiply. I'm allowed to cross multiply. If I'm cross multiply, I have s1 times 1 plus x2 equal to x2 times 1 plus x1. Distribute, I have s1 plus s1 s2. Distribute s2, I have s2 plus x1 x2. If I subtract both sides by x1 s2, I have s1 equal to s2. Since in both cases I get s1 equal to s2, then f must be 1 to 1. Since in both cases I get the same answer, get the same conclusion, S1 equal to S2, then F must be 1 to 1. Next, we try to prove that F is onto. Let Y be an element in the codomain. Then either Y is greater or equal to 0 or Y is less than 0. There are two cases. Case 1. If Y is greater or equal to 0, since the second piece of the function is positive, I try to find an x from the second piece of the function here. I try to find an x from second piece of the function. So if my y is x over 1 minus x, I try to find x, solve for x from this equation. I can rewrite y as y over 1. Cross multiply, distribute. I'm solving for x, so I move this term over. Factor x out, then divide both sides by y plus 1. So I get x equal to y over y plus 1. The x equal to y over y plus 1. Does this x satisfy this condition? Does this x satisfy this condition? Let's verify. Since y is greater than or equal to 0, then y plus 1 is strictly greater than 0. The top is non-negative. The bottom is positive. Non-negative number divided by positive number is always greater than or equal to 0. So we know this x is greater than or equal to 0. Is this x less than 1? Is this x less than 1? The top is y. Bottom is y plus 1. Bottom is always greater than or equal to top. Since the bottom is larger than the top, and they are both positive, then this number must be less than 1. Smaller number divided by larger number must be less than 1 if they are both positive. Smaller number divided by larger number must be less than 1. So this x is between 0 and 1. Therefore, it's between the interval from -1 to 1. Then for f of x, you plug in y over y plus 1. For f of x, we plug in y over y plus 1. Since y plus y over 1 is between 0 and 1, we plug into the second function. That equal to y over y plus 1 over 1 minus y over y plus 1. We can simplify the denominator first. Denominator number 1 can be rewritten as y plus 1 over y plus 1 minus y over y plus 1. They have same denominator, we combine the numerator, y plus 1 minus y minus y plus 1 minus y is number 1 over y plus 1. Y plus 1 minus y is 1. Then when we divide two fractions, we keep the top, flip the bottom over. That equal to y over y plus 1 times y plus 1 over 1. Cancel y plus 1. I get y. So f of x equal to y. Case 2. Y less than 0. If y is less than 0, since the first piece of the function is less than 0, we can try to obtain x from the first piece. In the first piece of the function, I can try to let y equal to x over 1 plus x. Then y can be rewritten as y over 1 cross multiply y times 1 plus x equal to x. Distribute y, I get y plus xy equal to x. Move sy over, y equal to x minus sy. Then I can factor s out. Divide both sides by 1 minus y. So I can let x equal to y over 1 minus y. Is this x satisfy this condition here? Does this x satisfy this condition? Let's verify. Y is less than 0. Y is strictly less than 0. 1 minus a number less than 0. 1 minus a negative number is positive. Y by itself is less than 0. Negative number divided by positive number is negative. So we know that this x is less than 0. Is this x greater than negative 1? Is this x greater than negative 1? This x can be rewrite as negative y over 1 minus y. The top positive y can be written as negative y. That can be rewrite as negative y over negative y plus 1. On the bottom, I write negative y in the front. Now observe this number. Since y is less than 0, negative y will be positive. Negative y will be positive. And positive number, negative y plus 1, is greater than negative y. Since both top and bottom are positive, and the denominator is larger than numerator, then negative y over negative y plus 1 will be less than positive 1. Since both top and bottom are positive, and the bottom is larger than the top, this expression is less than 1. But if I multiply both sides by negative 1, negative y over negative y plus 1 will be greater than negative 1. If I multiply both sides by negative 1, the direction of inequality change. So this expression is greater than negative 1. This expression is the same as x. So x is greater than negative 1. X less than 0, greater than negative 1. So we verify that this x is between negative 1 and 0. And negative 1 and 0 is a subset of the domain. That means x belongs to the domain. Then let's verify f of x equal to y. F of x is f of y over 1 minus y. Since y over 1 minus y is between negative 1 and 0, we plug y over 1 minus y into the first function, first piece of the function. That equal to y over 1 minus y (1) plus y over 1 minus y. Y over 1 minus y over 1 plus y over 1 minus y. Let's simplify denominator first. I have y over 1 minus y. Number 1 can be rewrite as 1 minus y over 1 minus y plus y over 1 minus y. The numerator stays the same, y over 1 minus y. For the denominator, we try to combine these two fractions together. I have 1 minus y plus y, which is 1 over 1 minus y. Then when we divide two fractions, we keep the first fraction the same, flip the second fraction over. Y over 1 minus y times 1 minus y over 1, which is y. So in both cases, we find an x and make f of x equal to y. That means f is on 2. Since f is 1 to 1 and on 2, f is a bijection. Hence, since f is a bijection, then these two sets has the same cardinality. Now, can we answer the question? Is the set of all real numbers countable or not? Can we answer the question now? Is the set of real numbers countable or not? We know that cardinality of the interval 0 to 1 is the same as any open interval a to b for all real number a, b. So that cardinality of the interval 0 to 1 is the same as the cardinality of the interval from -1 to 1. So these two intervals have the same cardinality. Also, we just proved that cardinality of the interval -1 to 1 is the same as the cardinality of the interval from net infinity to infinity. This set is the same as real number. Interval from net infinity to infinity is the same as real number. Interval from net infinity to infinity is the same as the set of all real numbers. Therefore, since cardinality of the set 0, 1 is the same as cardinality of the set -1 and 1, and cardinality of the set -1 and 1 is the same as cardinality of the set of all real numbers, then we know that cardinality of the set 0, 1 is the same as cardinality of the set of all real numbers. Since we know that the interval 0 to 1 is uncountable, then the set of all real number is also uncountable. So keep in mind that the set of all real number is uncountable. The set of natural number, integer, and rational number, they are countable. Next, let's look at a theorem. Every subset of n natural number, every subset of natural number is countable. Every subset of natural number is countable. Let's try to prove it. Let S be a subset of n. Let S be a subset of natural number. Then there are two cases. S could be either finite or infinite. Let me show you some examples about finite and infinite subsets. So n is the set of natural number. It's the set of 1, 2, 3, 4, 5, and so on. Let me show you some example of subsets. For example, give any three random number. S could be 99, 20, 36. That's a finite subset of n. That's a finite subset of n. Or it could be 1999, 998, 102, 101, 100. That's a finite subset in N. That's a finite subset in N. So they are finite subsets. And subset of N could be infinite. For example, if I let S be the set of all even natural numbers, or let S be the set of all positive even numbers, positive even number contains 2, 4, 6, 8, 10, and so on. This is an infinite subset. This is an infinite set, and it's a subset of N. If I let S be the set of all prime numbers, and we know that there are infinitely many prime. All prime is natural number. There are infinitely many prime numbers. And they are called infinite subsets. They are called infinite subsets of N. So a subset of natural number could be either finite or infinite. There are two cases. Let S be a subset of N, then there are two cases. S could be either finite or infinite. Case 1. If S is finite, is finite, then it's obviously S is countable. Then S is countable by definition of countable sets. That's case 1. If S is finite, then it's obviously countable. Case 2. If S is infinite, then in order to show that S is countable, we must show that S and N has the same cardinality, which means we need to show that there's a bijection between S and N. Now, how do we find a bijection between these two sets? Let me define a function like this. Let f be a function from N to S, be defined as f of 1 equal to the smallest element in S. Let f of 2 be the second smallest element in S. Let f of 3 be the third smallest element in S. And so on. Since S is an infinite set, I can assign all natural numbers to some numbers in S. Since S is an infinite set, I can assign all natural numbers to some numbers in S. Now let me show you this process using an example. It will make more sense to you. Let me show you this process using an example. It will make more sense to you. For example, S is the set of all prime numbers, for example. Then S is the set of all prime numbers. I can write S as 2, 3, 5, 7, 11, 13, 17. That's the set of all prime numbers. N is the set of all natural numbers. 1, 2, 3, 4, 5, 6, and so on. This function f assigns f of 1 to the smallest element. The smallest element is 2. So in this example, my f of 1 is 2. I assign f of 2 to the second smallest element. I assign f of 2 to the second smallest element in S. So here I assign 2 to 3. I assign 3 to 5. I assign 4 to 7, and so on. This is an example how my function f looks like. This is an example about how my function f looks like. I assign f of 1 to the smallest element to S. F of 2 to the second smallest element in S. F of 3 is the third smallest element in S. That's an example how function f works. Next, let me explain to you the reason this function f works for all subsets S. Let me show you the reason. The reason is because of something called well-ordering principle. Well-ordering principle says any subset of every subset of natural number has a least element. Every subset of natural number has a least element. Say, let S be a subset. For example, 1, 7, 9, 12, 15. For example, that's any subset S. That's any subset S of natural number. By well-ordering principle, there's a least element. I assign f of 1 to the least element. Then I remove this assigned element. What's left here is also a subset of natural number. If I remove 1, what's left is also a subset of natural number. Then I can also find, in this new subset, I can also find the smallest element, which is 7. I assign 7 to f of 2. Then I remove 7. In my new subset, this is also a subset of natural number. And in this subset, by well-ordering principle, there's a least element. I assign the least element to 3. Then after I assign this element, I remove this element. Then this is another subset. I assign the least element to the next one. So when you look at this process over, we can see that I assign f of 1 to the smallest element. I assign f of 2 to the second smallest element. I assign f of 3 to the third smallest element, and so on. So the reason I'm allowed to do this assignment is because of the well-ordering principle. That's how I define function f. And by this definition of f, we can see that f is an increasing function. F assign 1 to the smallest element, 2 to the second smallest element, that's a little larger than the first one. F assign 3 to the third smallest element, that's a little larger than the previous one. So we can see that f is an increasing function. So by this definition, we can see that f is an increasing function. If I define f like this, then f is an increasing function. Next, let's try to show that f is one-to-one and onto. First of all, let's try to show f is one-to-one. A function is one-to-one. The definition says for all S1, S2 in A, if f of S1 equal to f of S2, then x1 equal to S2. That's one way to write definition. Another way to write definition is for all S1, S2 in A. If S1 doesn't equal to S2, then f of S1 doesn't equal to f of S2. These two statements are equivalent because they are contraposition of each other. These two statements, they are contraposition of each other, so they are equivalent. We can show one-to-one using either way. In this problem, using the second definition will be much easier. So let's show f is one-to-one. Let S1, S2 belong to the domain. Assume S1 doesn't equal to S2. Assume they are not the same. We use the second definition. Assume they are not the same. Then we have two possibilities. Either S1 is less than S2 or S1 is greater than S2. We have two possibilities. Either S1 is less than S2 or S1 is greater than S2. If, case 1, if S1 is less than S2, then since f is a increasing function, f of S1 is less than f of S2. The larger number I plug in, the larger it is. F is an increasing function. The larger number I plug in, the larger it is. Then similarly, if x1 is greater than S2, then f of S1 is greater than f of S2. In both cases, f of S1 doesn't equal to f of S2. So f is one-to-one. Next, we try to show that f is onto. So let y belong to the codomain. We try to show that there is an x in the domain such that f of x equal to y. Let y belong to S. Since S is a subset of natural number, that's how we define S. S is a subset of natural number. Then y is a natural number. A natural number must be finite. So y is finite. Since y is a finite number in the set S, since y is a finite number in S, no matter how large it is, we will be able to count y in the set. No matter how large it is, since y is finite, we are able to eventually assign y. So, since y is finite, then there exists a n in N such that y is the n smallest element in S. Since y is finite, then there must exist an n in N such that y is the n smallest element in S. So f of n equal to y. And in general, we can replace n with letter x. In general, we can replace n with letter x. So there exists x in N such that y is the x smallest element, such that so f of x equal to y. So there exists x in N such that y is the x smallest element in S. So f of x equal to y. So since I can find an x in a domain such that f of x equal to y, then f must be onto. Since f is one-to-one and onto, then we know f is a bijection. Therefore, f is a bijection. Since there's a bijection from n to s, then cardinality of n and s must be the same. Hence, cardinality of s equal to cardinality of n. Since cardinality of s equal to cardinality of n, then we know s is countable. So s is countable. So that's a proof for the theorem that every subset of natural number is countable. That's the proof. Next, let me introduce a theorem. If a set is countable, then all its subsets are countable. If a set is countable, then all its subsets are countable. Let's prove it. Let A be a countable set. And let B be a subset of A. Let A be a countable set, and let B be a subset of A. We try to show that B is countable. First of all, let's look at a simple case first. First case, A is finite. If A is finite, then since B is a subset of A, B must be finite. Since B is finite, B must be countable. That's the definition of countable set. If B is finite, B must be countable. That's case 1. Case 2. A is infinite. If A is infinite, then there are two possibilities. B is a subset of A. B could be finite or infinite. If A is infinite, B is a subset of A. B could be finite and B could be infinite. Let's look at first case. A is infinite and B is finite. If A is infinite, there are two cases. B could be either infinite, could be finite or infinite. If B is finite, then B is countable. That's case 2, also simple. Case 3, A is infinite and B is an infinite subset of A. Since A is infinite and A is countable, since A is countable and infinite, then A has the same cardinality as natural number. Since A is countable and A is infinite, then A has the same cardinality as natural number, which means there exists a bijection F from A to N. Since A is countable and infinite, A has the same cardinality as natural number. So there exists a bijection between two sets. There's a bijection F from A to N. In this problem, we try to show that the infinite set B is countable. That means we need to show that set B has the same cardinality as the set of natural numbers. So let function G from B to N be defined as G of X equal to F of X for all X in B. And since B is a subset of A, every X in B belongs to A, and F assigns each element in A to a natural number. So this function is well defined for all X in B. This function is well defined. Now next, let me try to show that this function G is one-to-one. So let S1, S2 belong to the domain. Assume G of S1 equal to G of S2. In order to show G is one-to-one, we must show that S1 equal to S2. So assume G of S1 equal to G of S2. Since S1, S2 belongs to B, G of S1 is the same as F of S1, and G of S2 is the same as F of S2. So F of S1 equal to F of S2. Since G of S1 equal to F of S1 and G of S2 equal to F of S2. Since F is a bijection, then if F is a bijection, F must be one-to-one and onto. Then F is one-to-one. Since F is one-to-one, F of S1 equal to F of S2, that implies S1 equal to S2. So X1 equal to S2. Since F is one-to-one, F of S1 equal to F of S2, that implies S1 equal to S2. Since G of X1 equal to G of S2 implies S1 equal to S2, then G is one-to-one. Now, in the beginning of the class, earlier of the class, I proved a theorem that says if F is a one-to-one function, then cardinality, if F is a function from A to B, and F is one-to-one, then cardinality of A is the same as the cardinality of the range. Cardinality of A, cardinality of the domain is the same as the cardinality of the range. Same thing here. This function G is a one-to-one, so cardinality of the domain is the same as the cardinality of the range. Since G is one-to-one, cardinality of the domain is the same as cardinality of the range. Then, since G is a function from B to N, its range is a subset of its codomain. Since range of G is the subset of its codomain, and its codomain is N, then we know that G of B is a subset of N. G of B is a subset of natural number, and the previous theorem says every subset of natural number is countable. So by the previous theorem, we know that every subset of natural number is countable. We know that G of B is countable. Since g of b has the same cardinality as b, and b is infinite, g of v must also be infinite. If an infinite set is countable, it must have the same cardinality as a natural number. So, cardinality of g of b must be the same as cardinality of natural number, since it's infinite and countable. Then, since b has the same cardinality as g of b, and g of b has the same cardinality as the natural number, then we know that b has the same cardinality as natural number. Since b has the same cardinality as natural number, then b is countable. Let's complete the proof. Next, based on the previous theorem, we have a corollary. Let's say if a set has an uncountable subset, then the set itself must be uncountable. If a set has an uncountable subset, then it must be uncountable. Let's prove it. The proof is simple. We try to prove by contradiction. To show a set is uncountable is not easy. So we try to prove by contradiction. Prove by contradiction. Let A be a set and let B be an uncountable subset of A. Prove by contradiction. Assume A is countable. We try to prove A is uncountable. Assume A is countable. Since B is a subset of A, then by the previous theorem, a subset of a countable set must be countable. By the previous theorem, a subset of a countable set must be countable. Then, by the previous theorem, B must be countable. But we assume B is an uncountable subset. That's a contradiction. So B must be uncountable. So A must be uncountable. That means our assumption was wrong. So A must be uncountable. Note, since the interval 0, 1 is uncountable, and the interval 0, 1 is a subset of real number, then by the above corollary, we can tell that the set of real number is uncountable. If If a set has an uncountable subset, then the set itself must be uncountable. So the set of real number is uncountable. Using this theorem, this corollary, we can prove that a set of real number is uncountable in an easier way. The previous way may be too hard. This way is easier. Next theorem. We try to prove that the union of two countable sets is countable. The union of two countable sets is countable. Let's prove it. Let A and B be two countable sets. Here we can assume A and B, they are disjoint. Or if AB is not disjoint. If A and B is not disjoint, I can separate A union B into two pieces. A and B minus A. If they are not disjoint, I can separate A union B into two pieces. Set A and set B minus A. These two sets are disjoint. So if A and B are not disjoint, let A prime equal to A and B prime equal to B minus A. Then we can see that they are disjoint and they are union. Then A prime and B prime are disjoint. And A prime union B prime is the same as A union B. Then we can see that A prime and B prime, they are disjoint. If I combine two sets, I still get A union B. The proof is simple. A prime intersection B prime. A prime intersection B prime. A prime is A. B prime is B minus A. B minus A can be rewritten as B intersection A complement. So for intersections, I can apply associative law and commutative law. It can be rewritten as A intersection A complement. Here we use a bar for complement. In this class, we use a bar for complement. Apply associative law and commutative law. A intersection A complement, intersection B. And we know A intersection A complement. A intersection A complement. What's between A and A complement is nothing. So that's NP set. NP set intersection B. What's common between NP set and B? That's NP set. So we can see that A complement and B complement, they are disjoint. A complement union B complement do the same thing. A complement union B, A prime union B prime. It can be rewritten as A union B prime is B minus A. B minus A can be rewritten as B intersection A complement. Then apply distributive law. I have A union B intersection A union A complement. A union A complement is the universal set. If I combine A and A complement together, I get a universal set. And every set take intersection with universal set, I get a set itself. For every set, if I take intersection with the set and the universal set, I get the set itself. That's what's common between this set and the universal set. So we can see that A prime and B prime are disjoint. If I choose A and B to be this, A prime and B prime, they are disjoint. A prime union B prime is A union B. So if A and B are not disjoint, I can use A prime B prime instead of A. I get the same conclusion. So assume, here we can assume A and B are disjoint. If not, if A and B are not disjoint, let A prime be A and B prime be B minus A. Then A prime and B prime is disjoint. A prime and B prime are disjoint. And A prime union B prime is the same as A union B. So if A and B are not disjoint, we can use A prime and B prime instead of A and B, where A prime B prime are disjoint, and A prime union B prime is the same as A union B. So to make the problem easier, we can assume set A and set B are disjoint. Next, we try to show that A union B is countable. Now, for set A and set B, since they are countable, it could be either they could be either finite or infinite. So there are three cases. First case, A and B, they are both finite. Second case, they are both infinite. Third case, one of them is finite, one of them is infinite. So for set A and set B, there are three cases. They are either both finite, one of them is finite, one of them is infinite, or they are both infinite. There are three cases. Let's look at the first case. Case 1. Both A and B are finite. Case 1. Both A and B are finite. If they are both finite, then cardinality of A equal to n, and cardinality of B equal to m, where m and n are non-negative, they are non-negative integers. Then the cardinality of a set must be non-negative integer. It must be integer and it must be greater than or equal to 0. Then by rule of cardinality, by rule of cardinality, since A and B are disjoint sets, cardinality of A union B is the same as cardinality of A plus cardinality of B. By rule of cardinality, if A and B are disjoint sets, cardinality of A union B is the same as cardinality of A plus cardinality of B. That's m plus m. And integer plus integer is integer. Integer plus integer is integer. And positive number, non-negative number plus non-negative number is non-negative. So A union B is finite. Since it's finite, it's countable. That's case 1. If they are both finite, then A union B is countable. Case 2. One of the set is finite. So either A is finite, B is infinite, or A is infinite, B is finite. The proof for these two cases has no difference. So let's assume A is finite and B is infinite. Let's assume A is finite, B is infinite. If A is finite, then there are two cases. A could be either empty or non-empty. If A is empty, then A union B is the same as empty set union B. Let's set B. Since B is countable, then A union B is countable. That's a simple case. Now, if A is not countable, if A is not empty, then A has some cardinality n, which is a natural number. If A is not empty, then the n being the cardinality of A, n must be some positive integers. So n is a natural number. Then, since A has cardinality n, then there exists a function f. There exists a function f, then map n integers to A, where f assigns n integers, f assign integers 1 to n to n distinct elements in A. Here f assign 1 through n to n distinct element in A. Since B is countable, B is infinite and countable, since B is countable and infinite, there exists a bijection, say G, from N to B. Next, we try to show that the set A union B is countable. Since A is finite, B is infinite, A union B must be infinite. If we try to show A union B is infinite, is countable, we must show that A union B has the same cardinality as natural number, which means we need to show that there's a bijection from the set of natural number to A union B. So try to find a bijection from the set of natural number to A union B. Let function H from the set of natural number to A union B be defined as h of x equal to f of x if x equal to 1, 2, up to n equal to g of x equal to g of x minus n if x equal to n plus 1, n plus 2, and so on. Next, we try to show that this function h is a bijection. It's 1 to 1 and on 2. Next, we try to show that this function h is a bijection. Let's first of all try to show that h is 1 to 1. Let S1, S2 belong to the domain. Assume g of S1 equal to g of S2. Assume assume h of S1 equal to h of S2. Then there are two cases. H of S1, they are either both belong to set A or they are both belong to set B. There are two cases. If they are the same, then they are either both belong to set A or they are both belong to set B, because we assume A and B are disjoint sets. So if h of S1 equal to h of S2, then they are either both belong to set A or they are both belong to set B. So there are two cases. Since A and B are disjoint, h of S1 equal to h of S2, they are either both belong to set A or they are both belong to set B. There are two cases. H of S1 equal to h of S2. The codomain is A union B. H of S1, H of S2, they are either both belong to set A or they are both belong to set B. Case 1, if they are both belong to set A, then both S1, S2 must be between 1 and n. Then S1, S2 must be between 1 and n. So for h of S1, I plug in S1 into function f. For h of S2, I plug in S2 into function f. Since f assigns integers 1 through n to n distinct elements, if they are the same, then S1 must be the same as S2. Since f assigns each integer to distinct elements in A, then S1 must equal to S2. Case 2. If h of S1 equal to h of S2 belong to set B, then S1, S2 must equal to some number greater than n, n plus 1, n plus 2, and so on. It must be some number, integers greater than n. Then, in this case, I plug in S1, S2 into function g. I plug in S1, S2 into function g. So I have g of S1 minus n equal to g of x2 minus n. Since we know g is a bijection, g must be 1 to 1. Since G is a bijection, G must be 1 to 1. So if G is 1 to 1, G of x minus 1 equal to G of s2. G of s minus 1 equal to G of s minus 2. That implies x1 minus n equal to s2 minus n. Since G is a 1 to 1 function, G of s minus 1 equal to G of s2 minus n. It must be the same as s1 minus n equal to x2 minus n. Then I can add n to both sides. So s1 equals s2. In both cases, we show that s1 equals s2. So h must be 1 to 1. So h is 1 to 1. Next, we try to show that h is onto. In order to show h is onto, let y belong to the codomain of h. We try to find x in the domain such that h of x equal to y. Since sets A and B are disjoint sets, so either y belong to A or y belong to B. There are two cases. Either y belong to A or y belong to B. Case 1. Y belong to A. Since function f assign numbers to set A, so I try to find x using function f. Since function f assign numbers to set A, we try to find x using function f. Since f assigns each of 1, 2, 3 until n, as f assigns each of these numbers to distinct elements in set A. Since f assigns these numbers to distinct elements in set A, and A has exactly n elements, then for y belong to A, there exists a x in the set 1, 2, 3 up to n, such that f of x equal to y. And we know that since x belong to 1, 2, 3 up to n, this is a subset of natural number, then we know that x belong to n, which is domain of h. So we find an x in the domain of h such that h of x, since x is between 1 and n, h of x equal to f of x, that equal to y. So if x belong to A, I find an x in the domain of h such that f of x equal to y. That's case 1. Case 2. If y belong to B, since function g assign numbers to set B, so I try to find x using function g. Since function g assign numbers to set B, if y belong to B, I try to find x using function g. Since g is a bijection, that's our assumption here. Since g is a bijection, then g is onto. Then g is onto. For y belong to B, since g is onto for y belong to B, there exists something in the domain. There exists something in domain of G. Let's use a different letter. There exists M in the domain of G, such that G of M equal to Y. Now we try to use function h to have Y. In function h, h of x equal to x minus n. So I try to have G of M. I try to have G of M. But here, if I use x, I must have x minus m. So in order to find x, I set x minus n equal to m. I set x minus n equal to m. I set x minus n equal to m. Then I try to find x here. If I add n to both sides, my x is m plus n. So, since n is a natural number, m is a natural number, then x equal to m plus n must be natural number. So x equal to m plus n belong to the domain of H. S equal to m plus n. S equal to m plus n belong to the domain of H. So h of x equal to h of m plus n. M plus n is clearly one of these numbers. It's larger than n. M plus n is larger than n, so we use function g here. For function g, I plug in m plus n for x. Since m plus n represents x, I plug in m plus n for x in function g. I have g of m plus n minus n. If I simplify, I got g of m equal to y. So if y belongs to B, I find an x in the domain of H. Such that h of x equal to y. Therefore, in both cases, since I find x in the domain such that h of x equal to y, so h is on 2. Since h is 1 to 1 and on 2, then h is a bijection. And we know that since h is a bijection from N to A union B, these two sets must have same cardinality. Since h from N to A union B is a bijection, they must have same cardinality. So A union B and N must have same cardinality. Since the set A union B and the set of natural number has the same cardinality, the set A union B is countable. Since the set A union B and the set of natural number they have the same cardinality, then the set A union B is countable. So, in case 2, if A is finite, B is infinite, A union B is countable. Case 3, A and B are both infinite. Both A and B are infinite. Since A and B are countable sets, if they are infinite sets, then they must have same cardinality as natural numbers. Since both A and B are countable, if they are infinite sets, then they must have same cardinality as natural numbers. Then, since A and B are countable, then they must have same cardinality as natural numbers. Since A has same cardinality as natural number, then there exists a function f there exists a bijection f from n to a. Since B has the same cardinality as n, then there exists a bijection G from n to B. Since our goal is to show that A union B is countable. Since we try to show that A union B is countable, and we know A union B, they are both A union B is infinite, we must show that there's a bijection from natural number to A union B. Since both A and B are infinite, A union B must also be infinite. So if we want to show that A union B is countable, we must show that there exists a bijection from natural number n to A union B. Next, let's try to find a bijection. Let function h from natural number to A union B be defined as h of x equal to f of x plus 1 over 2 if x is odd, equal to g of h of x equal to g of x over 2 if x is even. For this function h, I try to assign every odd number in the domain to every element in set A. I try to assign every even number in the domain to every element in set B. I try to assign every odd number to elements in set A and every even number to elements in set B. So if I plug in odd number, if I plug in 1 plus 1 over 2 is 1. I have f of 1 here. If I plug in 3 plus 1 over 2 is 2. I have f of 2. If I plug in 5 plus 1 over 2 is 3. I have f of 3. So here, odd number, h assign every odd number to every element in set A because f map every integer to set A. And same thing, I try to assign every even number to set B, to every element in set B. If I plug in 2 over 2 is 1. I have g of 1. If I plug in 4 over 2 is 2. I have g of 2. So g assign every integers to elements in set B. So this function h assign every odd numbers to elements in set A and assign even numbers to elements in set B. Next, let's try to show that this function h is one-to-one. Let S1, S2 belong to the domain. Let S1, S2 belong to the domain. Assume h of S1 equal to h of S2. Assume h of S1 equal to h of S2. In order to show that h is one-to-one, we must show that S1 equal to S2. Now, h of S1, h of S2, there are two cases. Either they are both belong to A or they are both belong to B because h of x belong to A union B. So they are either both belong to A or they are both belong to B. A and B are disjoint sets. They are either both belong to A or both belong to B. So there are two cases. Case 1. Both of h of S1, h of S2, if they both belong to A, or h of S1 equal to h of S2, they both belong to A. Now, case 1. h of s1 and h of s2, they both belong to A. Since A and B are disjoint sets, then that means only function f assign elements to set A. That means x must satisfy the first condition. If h of x, h of s2, if h of s1, h of s2 belong to set A, then both s1 and s2 must satisfy the first condition. Then s1, s2 are both odd. If they are both odd, I plug in s1, s2 into function f. So f of s1 plus 1 over 2 equal to f of x2 plus 1 over 2. Since f is a bijection, then f is 1 to 1. Since f is a bijection, then f is 1 to 1. Then if f of s1 plus 1 over 2 equal to f of s2 plus 1 over 2, what's inside must be the same. Since f is bijection, the inside must be the same. So s1 plus 1 over 2 must be the same as s2 plus 1 over 2. Then I can multiply both sides by 2. Multiply both sides by 2. s1 plus 1 equal to s2 plus 1. Subtract 1 from both sides. s1 equal to s2. So that's case 1. Case 2. If h of s1 equal to h of s2 belong to B, since A and B are disjoint sets, we are only able to obtain elements in set B using function g. Since A and B are disjoint sets, we are only able to obtain elements in set B using function g. So if we use function g to obtain elements in B, then S must be even. So here, since h of s1 equal to h of s2 belong to B, both s1 and s2 must be even. Then s1, s2 are both even. If they are both even, I plug in s1 into function g. I plug in s2 into function g. So g of s1 over 2 equal to g of x2 over 2. Then since we know g is a bijection, then g must be 1 to 1. Since g is 1 to 1, g of s1 over 2 equal to g of s2 over 2, that implies that the inside must be the same. So s1 over 2 must equal to s2 over 2. If I multiply both sides by 2, I have s1 equal to s2. So in both cases, if h of s1 equal to h of s2, in both cases I show that s1 equal to s2. So h must be 1 to 1. So h is 1 to 1. Next, we try to show that h is on 2. So let y belong to the codomain. We try to find x in the domain such that h of x equal to y. Since A and B are disjoint sets, if y belong to A union B, then there are two cases. Either y belong to A or y belong to B. So there are two cases. Case 1, y belong to A. Case 2, y belong to B. So there are two cases. Let's deal with the first case first. Case 1, y belong to A. Since only function f assign elements to set A, we try to obtain an x using function f. We try to find an x using function f. since f is a bijection, then we know that f is onto. Since f from n to a is onto, then for y belong to a, there exists n in the domain such that f of n equal to y. Next, I try to find x in the domain of h such that to make h of x equal to y. So I have n plus 1 over 2 here. I have f of n here. If I try to make the inside the same, I set x plus 1 over 2 equal to n. I set x plus 1 over 2 equal to n. I can multiply both sides by 2. Subtract 1 from both sides. X equal to 2m minus 1. So since I try to make the parentheses look the same, so I let x equal to 2m minus 1. Let x equal to 2m minus 1. 2m minus 1, since n is an integer, 2 times m minus 1 is always greater than or equal to 1. Since n is greater or equal to 1, 2 times m minus 1 is also greater than or equal to 1. So 2m minus 1 belong to the domain. It's positive integer, so that belongs to the domain of h. And also we know that 2m minus 1 is odd. 2 times a number minus 1 is odd. So h of x equal to h of 2m minus 1. Since 2m minus 1 is odd, I plug in 2m minus 1 into the first function for x. I plug in 2m minus 1 into the first function for x. I have f of 2m minus 1 plus 1 over 2. If I simplify, I cancel 1 first. I get f of 2n over 2, which is f of n. And f of n equal to y. So in the first case, when y belongs to a, I found x in the domain of h, such that h of x equal to y. It's case 1. Case 2. If y belongs to b, since we only able to obtain b using function g, f and g are a and b are disjoint sets. We only able to obtain elements in set b using function g. So we try to find an x in the domain using function g. Since g is a bijection, then g is onto. So for y belong to b, there exists a m in the domain of g. There exists a m in the domain of g, such that g of m equal to y. Now I try to find x. In domain of f, in domain of h, such that h of x equal to g of m. So if I try to make g equal to g of m here, I need to make x over 2 equal to m. So I set x over 2 equal to m. If I multiply both sides by 2, I have x equal to 2m. So let x equal to 2m. 2 times the integer, since m is an integer, m is a natural number. 2 times the natural number must be greater or equal to 1. Greater than or equal to 1. So 2 times m is also a natural number. This x belongs to the domain of h. This x belongs to the domain of h. And we know that 2 times the integer is even. So 2m is even. So x is even. It's better to say x is odd. So x equal to 2m is even. Next, so h of x. Since h of x is 2m, I have h of 2m. 2m is even. 2m is even. Since 2m is even, I plug in 2m into the second function of h. Since 2m is even, I plug in 2m here for x. I have g of 2m over 2. Simplify, 2m over 2 is g of m. And we know g of m is y. So in case 2, I also find x in the domain of h, such that h of x equal to y. Since I can do this in both cases, I find x in the domain such that h of x equal to y, then h is on 2. Since h is 1 to 1 and on 2, then we know h is a bijection. Since function h from n to a union b is a bijection, then the set a union b and n must have the same cardinality. Hence, a union b must have the same cardinality as natural number n. Since I find a bijection from n to a union b, then these two sets, they must have same cardinality. Since a union b has same cardinality as natural number n, then I can say that a union b is countable. That complete the proof. When a and b are both finite sets, a union b is countable. When one of them is finite, the other one is infinite, a union b is also countable. And in case 3, when both a union b are infinite, they are countable. So that complete the proof. Next, let me introduce a theorem. If A is a countable set, and B is an uncountable set, then cardinality of A is strictly less than cardinality of B. Let's prove it. Since A is a countable set, then it's either A is finite or A has the same cardinality as natural number. Let's consider first case, if A is finite. Case 1, if A is finite, since B is an uncountable set, which must be infinite. Since B is an uncountable set, that's infinite. So clearly, cardinality of A is strictly less than cardinality of B. Since B is an uncountable set, B is infinite. So it's clearly that cardinality of A is strictly less than cardinality of B. A is finite, B is infinite. So cardinality of A is strictly less than cardinality of B. Case 2. A is infinite. if A and B are both infinite, and we want to show that cardinality of A is less than cardinality of B, we need to show that there's an injection, there's a one-to-one from A to B. So to show cardinality of A is less than cardinality of B, we must show that there's a one-to-one function from A to B. Next, let's try to find a one-to-one function from A to B. First of all, since A is countable, and A is infinite, then A must have the same cardinality as natural number. A must have the same cardinality as the set of natural number. Since two sets have same cardinality, then if two sets have same cardinality, then there is a bijection between two sets. Then there exists a bijection f from A to n. Since f is a bijection, f must be one-to-one. So f is a one-to-one from A to n. Next, let function b, let function g from n to b be defined as g of 1 equal to b1 in B for some element in B. Since B is infinite, since B is uncountable, it's an infinite set, it must be some element in B. So let g of 1 be some element in B. Let g of 2 equal to b2 in B, such that b2 is not the same as b1. Since B is an infinite set, I'm able to find an element other than b1. Since B is an infinite set, I can find a different element in B other than b1. I can find a different element. Assign g2 to the second element. g3, let g3 equal to b3 belong to B, such that b3 not equal to b1 and b2. Since B is an infinite set, I can find a third element as other than b1, b2. So continue the process. Since B is an infinite set, I can assign every natural number to a different element, to a distinct element in B. Since B is an infinite set, I can assign every integer, every natural number to a distinct element in set B. So that's how I define function g. By its definition of g, since I assign every element in the domain to a distinct element in set B, this function g is one-to-one. By the definition of function g, g assigns each natural number to distinct elements in B. Then, so G must be one-to-one. Since we assign distinct elements to elements, since we assign every natural number to distinct element in set B, then G must automatically be one-to-one. Let function h from A to B be defined as g of f. Let function h from A to B be defined as g of f, since both f and g are one-to-one. Since both f and g are one-to-one, then h must be one-to-one. So since there's an injection, there's a one-to-one from A to B, since f from A to B is, since h from A to B is one-to-one, then by definition of by the rule of cardinality, cardinality of set A must be less than or equal to cardinality of B. Also, since A is countable and B is uncountable, then their cardinality cannot be the same. If they are the same, A is countable, cardinality of A is the same as natural number. If A and B has the same cardinality, then B will have the same cardinality as natural number. B will be countable. So if B is uncountable, A and B cannot have the same cardinality. Otherwise, B will be countable. Otherwise, if they have the same cardinality, B will be countable. So that's impossible. If A is countable, B is uncountable, they won't have the same cardinality. So since cardinality of A is less than or equal to B, and cardinality of A doesn't equal to B, since cardinality of A is less or equal to cardinality of B, and cardinality of A doesn't equal to cardinality of B, then cardinality of A is strictly less than cardinality of B. That's the proof. Next example. We know that Q represents the set of all rational numbers. In some textbook, they use P represent a set of irrational numbers. In some textbook, they use P represent a set of all irrational numbers. Which set has larger cardinality? Rational number or irrational number? P or Q? Which set has larger cardinality? The answer is the set of irrational number has larger cardinality. Let's prove it. Show that the set of irrational number has larger cardinality than the set of rational number. Let's prove it. In order to prove the set of irrational number has larger cardinality, I will first of all try to show that the set of irrational number is uncountable. Then since it's uncountable by the previous theorem, it has larger cardinality than the set of rational number, since rational number is countable. So I first of all try to show that the set of irrational number is uncountable, proved by contradiction. Assume the set of irrational number is countable. Since the set of rational number is countable, then the union of countable set must be countable. If P is countable, since if P is countable, we know that Q is always countable. The union of countable set is countable. But the union of P and Q, if I put rational number and irrational number together, I get a set of all real number. But P union Q, when I combine rational number and irrational number together, I get all real numbers. I get a set of all real numbers. And we know that real number, the set of real number is uncountable. That's a contradiction. That's a contradiction. So P must be uncountable. Since P is uncountable and Q is countable, since the set of irrational number is uncountable and the set of rational number is countable, by the previous theorem, the cardinality of countable set is always less than the cardinality of uncountable set. So we have cardinality of irrational number is strictly greater than the cardinality of rational number. That's a proof.